So welcome everyone to join this event. Today, this is the final presentation for the X-Camp internship program together with Rice University, guided by Professor Lin. So Professor Lin, just wonder if you may take this opportunity to give a few sentences of introduction about the background for this program. We really appreciate your support on this. Otherwise, this is not going to happen. And also your student, Luke, he has been very dedicated the mentor for this program. In the past few months, he has spent every week for an hour on the mentoring for the students. That's also very appreciated.
Should I take over?
Please.
Okay, thank you. Hi, everyone. I'm Yingyang Lin, and as Dr. Guo already mentioned, I'm an assistant professor in the electrical and computer engineering at Rice. So maybe let me first briefly introduce my group's research. I believe most of you have heard about artificial intelligence and machine learning, which has made a tremendous amount of breakthrough in different aspects of intelligent functionalities. So one key challenge for us, because of those breakthroughs, our society are very excited about and expect machine learning and AI will make a lot of impact into our daily life. So one challenge for deploying machine learning and artificial intelligence into our daily life is those machine learning or artificial intelligence algorithms are very complex, while many of our daily life devices, for example, smartphone, wearables, have limited resource. So my group's research is trying to develop technique to reduce the cost in terms of energy and time of those machine learning and artificial intelligence algorithms so that we can bring those powerful intelligent functionality to our daily life to improve human life quality. So that's the high-level goal of my group's research. And then next, I hope to maybe briefly mention this program. And so I'm very glad to have collaborate with Dr. Guo's team to run this internship program. So our intention is, I think because as teacher, we always have passion to open the door for motivated students. So that's the initial thought. And through this program, we hope to provide opportunity to motivated students and to learn about cutting edge research. I believe this experience can motivate them in the next step study and also the college application, and also provide some positive impact to our next generation young men. So that's the high level goal. And then through this summer, the first time, the students were guided and introduced to learn about the cutting edge AI and machine learning algorithms transformer. Actually, my student and researchers at Facebook, at Google are actively, many researchers in the community are actively researching on this topic. The students have this opportunity to learn about the algorithm and the hardware implementations. I think this program turned out to be very successful thanks to the students' hard working and also Chong's excellent and a lot of effort to communicate among the students and between the students and Dr. Guo's team. And a big sense, of course, go to my student, Luke Zhang. He very generous and kind to commit regular time and effort to this run. He is really driving this first-time internship program and among his busy PhD schedule. So thank you all students and the Chong and Luke. Yeah.
Thanks, Professor Nin. So Luke, maybe you can give an introduction about kind of from your perspective, how students learn and how this may benefit probably for future students.
Yeah, definitely. Thank you, Professor Lin, for the introduction and the coordination. So as Dr. Lin mentioned, our group is dedicated in delivering the efficient solutions for right now the complex AI applications algorithms through means of either the algorithm compression, hardware acceleration, or some flexible tool generations. So, and in terms of specifically for these projects, so the motivation is one thing we like to let the students to get an experience of the cutting edge and the most frontier research in the AI. But at the same time, we also like to have a lot of brilliant students to help us in terms of research because we have a lot of projects open. So and then like for the students, I'm pretty sure like a lot of skilled students can definitely add in a lot of the help. And in terms of that, like to this specific project, the reason we choose transformers is because like as many of you may already know, like right now, like we have different kinds of types of models for different applications. For instance, the convolutional neural networks for the computer vision tasks. Right now, the transformers indeed like different from the other models. Transformers indeed show great versatility across different applications. And also recent studies found like their trade-offs between the accuracy and the hardware efficiency is indeed astonishing. So that's the reason we want to push forward research in transformers. However, the hardware support for the transformers indeed is still lacking. So we think it's a great opportunity for both us and the students to get a hands-on and explore the possibilities for the efficient transformer solutions, or namely transformers can be deployed on the drones. Yeah. And so throughout the process, the objective of this internship or the project is to first we want the students to get a feeling, as I said, to get a feelings and experience about what is the research like, especially in the very fast-paced and cutting edge AI field. But in the meantime, we would like to have students help us to in terms like explore the research areas we haven't even ourselves explored. Yeah. And throughout the process, especially this project, because we are dealing with not only the software, but also the hardware level aspect. So students really can get a very low level detail about what the machine learning application is instead of just using a single line of code to execute it without knowing it. So yeah, so I think it can give students like a lot of like learning opportunities and understanding about the actual full spectrum or full stacks of the AI solutions. Yeah. So I think next the students can give a brief presentation and summary about the process of these projects and the outcomes. Yeah. Thank you.
Thanks, Luke. So the next slide is just the introduction slide for this project. So before students start, I will just make one more comment. So kind of for this project, the students have been working in the past probably about 3 months, dedicated while they still have some other program obligations. So consider the challenge of this program, Professor Lin and Luke mentioned, this kind of research, from my understanding, this is not the normal high school level research. This is more like close to at least undergraduate level research. So this requires probably harder skills and more mature students. So we'll see if we'll ask each student to give an introduction for themselves if they are available now. And this is the work coming off the team, and probably we'll only have some of students presenting the results here. And for all the parents and the future students, please don't worry if you do not understand all the details here. So that's something probably you'll get when you're higher level or along the learning process. And this is also, this is the first time we try this research program. So please feel free to provide the questions, comments, feedback later in the Q&A section. So before we start, for the students, we'll just ask each of you, if you are available, give a short introduction about yourself, which grade you are, school you come from, and what you have learned from XCamp and how that helped this program.
Hi, everyone. My name is Albert. I'm currently a junior at the Nueva School in San Mateo, and I think XCamp really helped prepare me for this program because it was a really great way of learning to code in C++ and also think algorithmically and think critically about efficiency. Like, it gave me an intuition for how to write the code used and how computers work in general.
Okay, so my name's Andrew. I've been coding at XCamp for 3 years now. I'm a sophomore at MDHS, and I like to thank XCamp for giving me an opportunity to learn in C++, which has helped me like do coding a lot.
Hi, I'm Ruth. I'm a senior at American High, and I think I was in XCamp for last half a year or so. And I want to thank XCamp for, it taught me a lot of the more advanced algorithms I need to get from USACO Gold to USACO Platinum. And it really helped me develop my computer science skills. So I'm really thankful for that.
And of course, XCamp has provided all of us with this opportunity to participate in the internship and do some real research. So I think we're all very grateful for that.
Okay, so if there are no other students for more introduction, we can start the presentation. So I will stop sharing here for the student. Student will share screen from your side.
All right, so as part of the XCamp internship program presentation, we'll be talking about transformers on drones, or the state-of-the-art ML onto lightweight devices. So we have 4 items in our agenda. First, we want to discuss the problem, which is a deep learning gap. Next, we want to talk about the solution, which is optimizing implementations. And then we'll talk about our process to implement the solution. And finally, the impact this will have in the future.
Let's start by discussing the problem. As with the current state of machine learning is that models are getting more accurate, but only by throwing more compute at bigger models. So for instance, a recent and popularized natural language processing model called GPT-3 was trained on 153 million books worth of data over 40 lifetimes worth of thinking by energy expended. The thing is, machine learning is the most impactful on edge devices. So things like smartphones, IoT devices, and autonomous vehicles, devices that we interact with in our daily lives. The reason for this is because these devices have to deal with the most uncertainty, because us humans and our human world is much more uncertain than the tightly constrained and documented worlds of, for example, APIs and all of the internet. For instance, a personal assistant running on your phone needs to be low power, and yet it needs to distinguish your voice from a crowded room or the noise of traffic. And robotic devices like autonomous vehicles need to deal with the monkey brains driving the cars around us, or disaster response robots might need to deal with objects falling and figure out, like, if it manipulates one item, what that item is holding up and how it might fall. The thing is, these devices have a really hard time leveraging the recent advances in machine learning, because once again, these recent models are based on really large models to squeeze a little bit of accuracy out. So what is the solution to this problem? Well, as with any engineering problem, we should consider the constraints first. The hard constraint for us is the memory limit, because IoT devices have maybe tens of megabytes of memory that can be used to store the model parameters and run inference. What we're optimizing for in our soft constraint is inference time. For instance, a robot that takes 10 seconds to figure out whether it can take a step forwards won't be very effective in real-time scenarios. But if we can speed up this inference by 100 times, then it'll be able to make 10 decisions per second and act in real time. In the literature, there have already been a number of optimization methodologies. For instance, model distillation is the process of converting the knowledge from a larger model to a smaller model. Weight quantization means truncating the last digits off a floating point number so that the answer might be less precise, but also the weights take less space to store. Architecture search aims to optimize the shape of models by removing low used weights. But we focus on hardware acceleration, which is designing custom hardware to support existing models. The thing about hardware acceleration is that it's probably the most difficult and time-consuming method, but it also leaves the most headroom to make an improvement. So why are current models so slow? Well, one reason is because they're often developed using machine learning frameworks, as you can see on the slide, which are generally based on Python. These frameworks are really flexible, which makes them great for machine learning researchers, but they are also not as efficient as they could be. What we're doing is we're trading off this development and research flexibility for efficiency. So we're spending a lot of time converting this code into harder to modify C and then translating that into an actual hardware description. So like making custom chips. And this allows the code to run much more efficiently, but it's also much harder to change the model architecture in case we need to. For this reason, we focus on a well-tested and verified model architecture called GPT-2, so that which we know works well for a lot of scenarios. Historically, these kinds of hardware transformations have increased inference speed by 500 times. So that's like saying a smartphone level processor would be 500 times slower than a dedicated chip that could go onto that edge device.
So how did we make it happen? What was our process? So our project had 5 main stages. The first stage, which is learn about hardware efficient transformers and just transformers in general. Next, we had to implement GPT-2 using vanilla Python with only NumPy as the library. And after that, we had to rewrite the implementation in C style so it could be put into high-level synthesis or HLS. Next, we generated the hardware description using HLS. And the final stage would be deploy the code to FPGAs on drones. All right, so the first challenge was transformers. Transformers are a pretty unfamiliar model to a lot of us, so we had to learn it by reading papers because we didn't know enough about it to implement it in low-level languages such as C. So as you can see here are some of the notes we took on transformers. There's a paper one of the papers that we read. And yeah, so an important part of transformers is attention. Attention is, you can think of it like this. Attention is how much attention each word pays to the words before it. For example, the word it pays a lot of attention to the and animal because it refers to the animal. So as you can see here, here's a technical diagram of how attention works. You might notice the 3 words query, key, and value show up. So you can think of it like this. Imagine you're trying to make a search algorithm for YouTube where someone can search a string and then they could find the video they're looking for that's relevant to their search string. So their search string would be the query, obviously. And the key could be tags on the video. Maybe if you search for cat videos, one video will have a tag of cat, another will have a tag of car. So the key and the query are combined to get the score, which determines how related they are. And then there's a value, which could be the actual video itself. The value is multiplied with the score, and then that is added up. All the stuff in the value, when multiplied the score is added up. So the larger the score is, the larger the final result is, and the more relevant it is. And here's a diagram of a basic transformer. First, there's input pre-processing, followed by an encoder, and the result from that encoder is fed to the decoder. And there's also output pre-processing and output post-processing. However, we did not use a vanilla transformer. We used a GPT-2 model, which only has transformers stacked on top of each other. Each decoder block has a mass self-attention followed by a feed-forward neural network. And we use GPT-2 small, which has 12 decoders. So our first task was coding GPT-2 in vanilla Python. So you might ask, if Python is so slow, why would you code in Python first instead of going straight to C? Well, the answer is Python's a lot easier to code and debug. So we wanted to verify that our idea was correct when we translated to Python, because translating from low-level Python to C is easier than just going straight from PyTorch to C. So our next task was coding GPT-2 in C. And the main challenge here was that we couldn't use a linear algebra library like we had in Python, which was NumPy. So we had to code a matrix structure that contained the data, the rows, the columns, and whether it was row major or not row major, which helped with transposing matrices. However, this had its own flaws. We couldn't use an HLS because in HLS, has certain limitations on the coding style, and it has to map the code into actual hardware. The structure cannot be interpreted by hardware ports while pointers can, so we couldn't use structures.
Here's an overview of HLS. What it essentially does is map C code to actual hardware on the FPGA. So this picture on the right is an FPGA, or field programmable gate array, that is actually running our GPT-2 inference. What an FPGA is it's a bunch of hardware modules that can add and multiply numbers, etc. And these modules can be turned on and off and linked together to do computations. A standard computer has a central processing unit which reads instructions and executes them one by one. Here we have a bunch of small modules which are very specialized. They can only do one type of instruction, but by connecting them together in the proper order, they can do all of our necessary computations automatically. And once again, high-level synthesis, or HLS, is the tool to translate from C to this hardware description. You can see here the utilization of our FPGA. So this is the area of our FPGA, and the blue cells are the computational units that are turned on. Programming for FPGAs is very different from programming for CPUs, which is what we are all used to coming from XCamp and USACO. One big difference is that there's no dynamic memory allocation, which means that we have to think very hard about where the inputs and outputs for each operation will live, because we can't just make new variables. There's also a lot more room for optimization. For instance, we don't have to worry about standard conventions for how big numbers should be. A lot of times people will use float 32 or float 64 because those are the standard sizes for floating point numbers, but we don't have to worry about that because it's custom hardware. We could have like 6 bits or 7 bits or 3 bits for a single weight. And finally, because we're on such a low level and the real world is messy, we have to worry about that messiness sometimes. For instance, a hardware clock actually can fluctuate by about plus or minus 15%. And if our clock is too fast, then we might not finish the computation in time and then have the ultimate race condition to debug.
So next up question is, how did we fix our GPT-2 code and make it like actually able to be used in HLS? So what we did is we took the different matrix things like the rows, the columns, and the row major and put them as parameters in each of the functions. This way, instead of using a matrix structure, we can just pass these as parameters. And instead of returning a matrix, we would just edit the data and return void.
Having written our code in C in a style that HLS can understand, it was time to do some optimizations. So here are some diagrams that we drew to help us understand how these optimizations work. In the top left, you can see an example of how a CPU would carry out this program, which is to add 4 numbers represented by these 4 circles. We have 2 types of instructions in the simplified model. The select instruction reads 1 number from memory, and the add instruction adds 2 numbers. Note that we have to use 3 add instructions because the add instruction can only add 2 numbers at a time. And these other purple circles are the intermediate values. Once again, we have to worry a lot about where the intermediate values will go. So you can see that while we only have 4 inputs, there is actually 6 rows worth of space required to do this addition. And finally, the x-axis represents the time needed. So the first select instruction would take this distance of time, and the full operation takes this width. In a normal CPU, only 1 instruction is executed at a time, which means that there's not much room for optimization. This is as fast as things can be. However, with FPGAs, we can do some more optimization. For instance, this technique is called pipelining, where essentially this block and this block of instructions are the same. But because this select instruction does not depend on this add instruction, we can run it at the same time. So here we've essentially moved this block back by 1 instruction, and we're able to finish the computation 1 instruction faster. Another type of optimization is called loop unrolling, where instead of doing different instructions at the same time, we do the same instruction at the same time. For instance, these 2 select instructions do not depend on each other. So here we're able to run both of them simultaneously. Notice that this means that we need 2 times the amount of hardware to run this select instruction. So when you unroll a loop, you have to use more hardware. We could combine these 2 techniques, unrolling and pipelining, by moving this select and add block forwards by 1 instruction, because again, this select instruction does not depend on the output of this add instruction. And finally, we can do even more aggressive unrolling, where we have 4 times the hardware, the select instruction hardware, and 2 times the add instruction hardware. And this is as optimal as this operation gets. So a lot of high-level synthesis and designing the FPGA after we've written our C code is working with this trade-off of speed versus hardware used. To recap, what we've done so far is we've learned about and understood this architecture model this neural network model called the transformer and specifically the GPT-2 variant. Then we've written the code to test our understanding in Python and translated that code into a dialect of the C programming language that can be automatically translated to a hardware description.
Okay, so our work is like helping create a more efficient and resource conservative AI that is like being deployed in like many aspects of our lives. So like when there's an emergency in like a storm or an earthquake, fast decisions have to be made in many unique situations, and that will help save more lives. And then for self-driving cars, they need to be electricity efficient and also need to react quickly in case of accidents. And then for devices that are on standby, they need to also be optimized for electric consumption. And another example of is data centers, where large amounts of computing is done and they need to save energy. And for this project, the GPT-2 model was simply chosen for its relative simplicity. But for each application, it has its own unique algorithms and architecture. Most of the time, these custom architectures are designed for speed or energy efficiency. But by evolving both the software models and the hardware components, many new doors will be opened.
Once again, we'd like to thank XCamp and Professor Lin for providing us with this opportunity, and also Luke for helping us on multiple months, meeting with us and answering our questions and explaining the concepts. Thank you for listening.
Thank you.